All right, so this is going to be the recitation for homework 5. If you've looked at the notebook, there's a notebook on hypothesis testing, a notebook on unsupervised learning, and the 688 notebook is on collaborative filtering. And collaborative filtering is, same size as before. Hypothesis testing is a little smaller, and the unsupervised learning notebook is heavier in terms of workload. So if you're going to leave something for the last minute, I would not advise leaving the unsupervised one as the last minute, especially because as we move on to more advanced algorithms, these more advanced algorithms are going to take more and more time to actually compute and show you any sort of result. Okay, so like we did things like naive Bayes. I think k-means is probably going to be the last thing that you do that's going to be like super fast, and then everything else from there on. SVM is also pretty fast in terms of machine learning algorithms. But then from here on out, a lot of the things that we do are going to take many, many iterations. Your code might take a couple minutes to run to get any sort of result locally. Don't worry about Autolab too much. We'll do a much reduced subsampling of the data set on Autolab, so it doesn't take that long to grade. But if you want to look at your results locally, you have to run it for a while. Okay. So I'll start with hypothesis testing. So in the hypothesis testing notebook, there's not a lot of new libraries here. It's really just using all the stuff that you've learned already to start doing hypothesis tests. And so basically, the main things you'll need is that you'll need to work with a Gaussian random variable and now a t-distribution. Both of these are still inside PyNotStats, so you can refer back to Recitation 4 notes for that. You can ignore my emails. And as a reminder, you will need to use the inverse CDF function. So if you recall, the inverse the CDF function gives you the probability that a random variable is at most this number, and then the inverse CDF function is the inverse of this function, right? So then you would need this to get, to turn a probability into a value for which the probability is equal to that. The CDF is equal to that. Remember from the probability lecture. So just a reminder, this function is called PPF. So if any of you actually figure out what PPF stands for, because it doesn't seem like it would stand for inverse CDF, but if you figure out what PPF stands for, I'm curious. So I don't actually know what it stands for. So same deal as before. We import scipy.stats as st. We can create normal random variables. We can create t-distributions. Important to note, the t-distribution takes in a number of degrees of freedom, right? So you need to pass this in as a parameter. Usually the degrees of freedom is the number of examples that you have minus 1. And then you can call the PPF function and give it a number, a probability number, and then it gives you exactly the value such that probability x is less than that number. Probability that x is less than the returned value is equal to the number that you gave it. Okay? So if that sounds confusing, just go back to your probability notes, figure out what CDF is, and then this is just inverse of that function. Okay, so this should be a relatively straightforward notebook. Same, just data is in a pandas data frame. You may find it interesting, and I would suggest that you do this one actually first if you want to stay relevant with what's going on in the United States with the presidential election, because the data set is poll results for the election. So then you're going to construct confidence intervals and do hypothesis tests on, who's going to win in these various states, and and you'll do that all by yourself by combining these different poll results and creating these statistics, calculate p-values, and see how confident these results are. Okay. So the remaining 2 notebooks are more standard in terms of more machine learning algorithms. And so we're going to go back to pandas again. I'm sure some of you don't have very fond memories of pandas. Well, before I move on to pandas, any questions on hypothesis testing? Should be relatively straightforward. There is a question right now on Piazza about asking what's the equation for the weighted variance. I don't actually know. I have to ask Divya. So we'll get back to you guys as soon as we figure that out. But all the equations for the weighted variance are basically the same. I think there's just 2 variants. One is biased, one is unbiased. So all that changes is the fraction. You only multiply by 1 over n, or you multiply by 1 over n minus 1. So in the end, it should be a relatively simple change as soon as we figure out which one it is that we want you to do. But it really shouldn't change your results that much. Okay. Okay, so now go back to pandas. Okay, so you're going to have to do a whole bunch of SQL-like queries on your pandas data frame. Like you want to pick out rows of your pandas data frame where some column value is equal to something else. In case you never figured that out or you never looked it up and you were just looping through the data frame, you can actually do these kinds of queries just by passing a Boolean array to it. So here we take the column A, we turn it into a Boolean array where it's true if it's greater than 0, and then we can pass this back into the data frame to get all the rows where the column A is greater than 0. Okay? So no need to iterate through your data frame, just do this if you want to select rows where A is greater than 0. You can combine multiple queries together, so you can have A is greater than or equal to 1, and then AND it with B is less than -2, right? And then this will select all the rows that satisfy these two conditions. Okay. And then there's also you can get the unique values of a column with the unique function. So hopefully this is all a review for you. But if you didn't figure this out already, then now you know. Okay. All right. So pandas data frames are array-likes. So you may have noticed that in our signatures we've been writing array-like, which may have been a mistake because not many people understood what an array-like was. And an array-like is basically anything that NumPy treats as an input to their function. So NumPy works not only on its own base arrays, but it works on anything that it considers an array-like. And in particular, data frames are array-likes. So you can pass data frames into NumPy, and it'll have exactly the result that you would expect it to be, right? So we can take the data frame, we can do numpy.sum, we can do numpy.multiply. We can, of course, if you want to skip all this data frame nonsense and just go back to NumPy, you can just call the asMatrix function and forget about all the headaches that pandas gives you. So usually, actually, you would normally do the asMatrix call as soon as you're done generating your features, right? Because as soon as we're done generating our features, then we usually treat the feature matrix is just now a matrix. We don't really care what it's called anymore. We just feed it now into our learning algorithms. So at that point, you can just drop the data frame structure and turn it into a matrix. But the reason why we use data frames is because it's very useful when creating these features, right? Instead of if you had all your data stored in the matrix already, then which column corresponds to like Monday? I don't know, maybe it's column 8. So the reason why we use data frames is that we can say data frame of Monday to get that column. But then as soon as we're done generating features, we can drop all of that. Did you have a question or no? Okay. Okay. Any questions about that?
What is the difference between the asMatrix and the values?
Asmatrix and values.
Just df of values.
So df dot values.
Or there's no parentheses.
They look exactly the same. So I guess one's a function and one's an attribute. This might actually be the underlying values of this data frame. So if you change df.values, you might actually be changing the data frame. asMatrix may not do that. We can check. So we can take df values 0 and set that equal to 0. Yeah, so changing df.values changes exactly the underlying data frame from this short experiment. I think if we do this, actually, asMatrix also returns the underlying matrix. So actually, both of these do exactly the same thing. So you can pick whichever one you want. If you prefer calling a function, you can use asMatrix. If you prefer accessing an attribute, then you can use dot values. It looks like they do exactly the same thing.
So what does the end of 0, 1, comma do?
There didn't need to be a comma there. Yeah. Was that your question?
Yeah.
Yeah, there didn't need to be a comma. But it's because a tuple. I think you can end tuples in commas, and then this is equivalent to this because the input here is just a tuple. Okay. Any other questions? Yeah. All right. Okay, so the last thing we're going to go to is NumPy tricks and performance. And the reason why, okay, well, I say this is the last thing, but this is like actually, you can tell by like this, if you look at the scroll bar on the side, it's actually just like the remaining 2/3 of this notebook. So by last thing, it is, the last major section. But, this is pretty important because now that we're moving on to algorithms that take a long time to compute, if you start doing things that are inefficient in there, instead of taking minutes as opposed to seconds, it'll take days instead of seconds. Okay. Well, actually, days instead of like minutes. Okay, so from seconds to minutes, we're now going from like minutes to days. So it's pretty important that you start writing. This is the reason why we make a big deal out of you writing efficient code in the beginning, because it's much easier to mess up on these easier examples and figure out what was going on wrong, as opposed to trying these much more complicated algorithms, messing up, and not being able to find out what's wrong because it takes forever to ever see anything happen. Okay. So actually for both of the assignments, for both the unsupervised learning assignment and for collaborative filtering, we have actually greatly reduced the data sets that we gave you so that it runs on the order of minutes. Okay. The full data set would not run on the order of minutes at all. Okay, that's just the state of machine learning and data science. So the ratings matrix that we give you for the collaborative filtering problem, the original data set has 24 million ratings. I believe we give you around 100,000 of them. So scaled down by like 240, a factor of 240 ratings. And the unsupervised learning problem, we give you a data set of about, I think, 600 images, 600 or 700 images of people. There's definitely a lot more than 600 or 700 images of people in almost every single image data set. So, but we've greatly reduced it because this is an assignment and they're not actually, this is for learning, okay? But it'll still take minutes. It'll still take minutes. Okay. And one aside from the last recitation is that numpy.new axis is actually equal to none. So it's just none but renamed. Just an interesting side note because that came up last time. Okay. Any questions before we start? Okay. So just this first part's actually not really a performance thing. It's just a nice notation thing. You can iterate over matrices in a sort of list manner. So NumPy has this kind of list like indexing method. So you can give it like an index, and it'll give you for example, in a two-dimensional array, it'll give you that ith row. So for example, here, x of 0 is going to give you the 0th row. If you do x transpose of 0, that gives you the 0th column. You can iterate over a matrix, so you can iterate over a two-dimensional matrix, and this will iterate over all the rows. Alternatively, if you want to iterate over the columns, then of course you just iterate over x transpose. And then if you want the index as well, you can just pass it to enumerate. Right? You can pass any list or iterable to enumerate, and it'll give you an index. So this is just mostly so that you can avoid doing like for I in range x shape 0, and then xi. Right? I'm sure most of you have probably written this for loop before. You don't need to. You can just do this. You can just do this guy. Or if you need I, then you can do this guy. Okay. It's not really. And it has also the benefit of you have less indices to worry about. So like if you have these double loops where you have like for j in range x dot shape 1, and then now you do xij, and you're doing math, and then like for some reason later on you have a typo, you're really tired, and you write xji. This messes things up, right? So it's much better to just do do this thing and then do for xij in xi. And then you'll always index ij the way you meant it to be. So simpler code will hopefully reduce the number of bugs that you have. Okay. Okay, so now back onto the actual performance stuff. So in general, you should pre-allocate your matrices whenever you can for NumPy. It is prohibitively expensive to be appending these matrices together, piecing them together from parts, because they are not constructed like lists. Right? Python lists, remember, they were built as unbounded arrays, so they're pretty fast to add on to if you want to put more things onto the list. But NumPy arrays are not lists. Okay, they are optimized for fixed shape operations. So what you should do is, for example, some people may have created a matrix by appending rows together. So you can do that like with a VStack, just adding row after row. Or some people made a list of rows and then called vmat or hstack or vstack. But this is very inefficient because every time it pieces something together, it has to reallocate the new space for that and then copy everything in. Right? It's not doing a simple operation like with the Python lists of just expanding it by a constant time cost operation. So it's actually doing something on the order of the entire size of the matrix. Okay, so instead of doing this thing, if you need to go row by row, you should instead pre-allocate the entire thing and then just assign the rows as you go. Okay, makes sense? It's a pretty simple optimization, but I guess I already ran this here, but you can see it's 45 times faster. Okay, so when things take seconds and then you start doing the wrong thing, then it takes 45 seconds, and now this is on the order of minutes, and this is no good. All right. Any questions? Okay. The other thing you should do is pre-allocate matrices that don't change. So, for example, you may have like this diagonal matrix that serves as a regularizer. Like this. This probably looks familiar. Like when we added lambda to the diagonal for SVM, or to any sort of covariance matrix. If we want to make it invertible, then we add something to the diagonal. If we're doing this a lot, then it makes a lot of sense to pre-allocate this matrix, especially if it's very large. Okay, because otherwise, if you do, within this loop, here we're just adding the diagonal to x, and here we pre-allocated it, and whereas here if I just use numpy.i of n, then it'll reallocate and recreate this identity matrix every single time. And so if n is on the order of thousands by thousands, this becomes a very expensive operation. Okay. And on just the order of 1,000, it's already twice as slow for just 10 operations. Okay. All right. Any questions about that? All right, great. We're moving along. Okay, so now we move on to pairwise distances. So if you remember we're like jumping around to all sorts of different things because I guess that's pretty much what I have to tell you guys. They're just like all these little random things. But so now we move on to computing pairwise distances. And so remember from k-means, you have to compute this, you have to find the minimum over all the centers of the distance to all the centers, right? Do you remember? This is familiar. It's like if we have our center is mu, then we take mu minus xi squared mu j, and then we want the min of all j, right? We want this thing, and then we want to do this for all j and for all I. So we need to compute this for this distance for all j and for all I. And as you can probably guess from the theme of today's lecture, where I'm telling you not to iterate over things, it's very inefficient to just iterate over every element and just compute this this distance. So you can do this, right? You know, now that you know this notation, it's not that complicated to write, but it's pretty slow to do this because NumPy is optimized for matrix operations, right? So you should use matrix operations absolutely whenever you can. So if you remember from the slides, he wrote like a line of code that computes all pairwise distances. If anybody remembers, it looked something like this. Is it familiar? Yes, no? Nods? This is from his slide. I took it directly from his slide. Well, I renamed centers to Y, but that's about it. No, this doesn't look familiar. So does anybody know? So I kind of want to show you guys how he came up, how he actually came up with this, because I guess like to you guys it sort of looks like matrix algebra voodoo magic. He computed all the pairwise distances between x and y in a single line without any for loops, right? So it's not actually that difficult to see why this is equivalent to the previous one. So I think I'll go through that so you guys understand how this works. So you can start turning your own equations that are not necessarily pairwise distances into matrix operations. Okay. So we have this thing. So we want to compute the matrix. So we want to compute this distance ij, which is equal to mu I minus xj squared, right? So mu I and xj are vectors, they're rows, so like this is mu, we got mu1 through mu k, and we got x, which is x1 through xn. Okay, so we want to compute dij for, so this matrix dij, where each dij is the distance from, actually let me switch this. And get xj to xi to j. There we go. So dij is the distance from example I to center j. Okay, and then once you have this, then you just take the once you have all the distances, then you can take the min over an axis to get the minimum distance, right? So how does this become that? Anybody have any ideas? Okay, so this 2 norm, right? This 2 norm is the same as so we have let's see. So if we have a vector x and we do the norm of x, this is x transpose x, right? So this is basically it. So we take this, so this is xi minus mu j squared is going to be equal to xi minus mu j transpose xi minus mu j. Okay, and now we just use distributive law. We get xi transpose xi minus 2xi transpose mu j plus mu j transpose mu j. Okay, this is starting to become looking familiar now. Okay, so now we have this term, and we've got this minus 2 of the cross product of the dot product of xi and mu j, and then we've got the norm of mu j. Okay, so now if we want to compute xi and mu j for all for all I and all j, right? So then this is xi is going to be some vector, and then mu j is going to be some column vector. So an easy way to think about this matrix algebra is that whenever you take something on the left, if you want to compute more things of it, you can just add more rows, right? So then this is xi and mu j. We could also do xi minus 1 mu j by just stacking it on top. Okay, so then this is a matrix of these 2 things. And then we could also add the mu j plus 1 over here, right? So this is like a way you can think about it. And then so when you multiply this, you'll get, this will be xi minus 1 mu j, xi minus 1 mu j plus 1, xi mu j, xi mu j plus 1. Right? So then this gives you those 4 spots. Right? So now we can just generalize this idea, right? This is just the X matrix. Right? We can now expand it to every single matrix X, every single element X, so now this is just X. And this thing is every column is just a row of mu. So this is just mu transpose. Right? So then mu trans X times mu transpose will give you xi mu j for all ij. Right? So that's where this middle term comes from, which is this part. So that's exactly what he's doing here. He's taking x dot mu transpose. Well, here I wrote y, but makes sense? And then you do actually exact same thing, or not exactly the same thing. He does a little thing here. So xi transpose is going to be, this. How can I say this? Yeah.
Why there's no broadcasting in line?
Is there no broadcasting in Y? There is. There is broadcasting in Y. Yeah. So we'll get there in a second. So this so the next thing he does is he has this like x squared. So that's that should give you some indication that that's this guy, right? So this xi transpose xi is just the sum of xi1, xi1, sum from xi1 to xi, however many things there are, like L. So it's just the sum over squares, right? So xi transpose xi is just the sum of the squares of all the components. So he's computing the squares of all the components here, and then taking the sum. So that's exactly this term, right? But now it's in a vector because he took the sum over one axis. He takes the sum over one axis and then reshapes it to be a vector. So then now it's going to take this x u transpose, and it's going to add this term to every row, right? So we're just adding this to every row. And then he does the same thing here. He takes the square of all the mu's, leaves it as a row. So then now he's going to add the mu to every column. Okay. So then this is this is every column. This is every row. This is the I. This is the j. Everything matches up. But it really just stems from the fact that you can rewrite the equation like this. This you can compute with a matrix multiply. This you can compute by just broadcasting over the rows. This you can compute by broadcasting over the columns. And that's exactly what it does. Okay, does that make sense? Are there any questions? Okay.
Can you briefly explain what is the square bracket non?
This thing. So this is so NumPy one-dimensional arrays don't have a second dimension. So row or column doesn't mean anything to them. It's just a one-dimensional array. So then when you broadcast over if you want to broadcast a row, then it's fine. It treats it as a row. But if you want to broadcast as a column, then the one-dimensional array is just always a row. So you need to reshape it to have this second dimension. So you can. So we can just say like, we can take this guy. So we have x, right? And then we take the sum over an axis. It's now a one-dimensional array. So then if you try to broadcast, it'll broadcast along the wrong dimension. So then we add this to make it a column vector. And so now it'll actually broadcast along every column. I think this is also explained in the other recitation as well. Yeah. Okay. Any questions? Okay. Another thing is NumPy has these min and argmin functions. You should use these judiciously. Okay. Please do not loop over your matrix to find the minimum element. It is both slow and may or may not produce the same answer as us. So just don't do that. because I think min and argmin will always return the first such answer, so just use min and argmin. It's faster and it's cleaner, and just use it. Okay, here's another trick that is actually prevalent in like almost all of machine learning, but nobody talks about it because they just expect you to look, realize that you're having numerical problems, then Google it, and then find out that you have to do this trick. I'm not doing this to you. I'm telling you that you have to do this trick now. So the problem here is, suppose you have a vector of values a, and you need to compute, this exponent. You're going to do this, remember like the softmax from MNIST. We're going to exponentiate every single value in a, and then divide it by the sum of the exponential values to turn this into a probability. Right? Does this make sense? To trigger some memories. So we want to turn these vector values a into probabilities, but we're going to exponentiate it so that it's like a softmax. So now, if we want to compute this directly, you can compute this directly, and if a is not that bad of a number, then everything will be perfectly fine. However, if a is a very large negative number, then you'll run into some problems. In particular, for example, if we just take, an array of negative 10 to the negative 10 to the 10, so like this is 10 billion. Okay, so negative 10 billion, and try to compute this value, then we end up with a whole bunch of nans, right? And why is that? Well, so we can do numpy.x of 1e to the 10, negative 1e to the 10. Sorry, the negative is on the outside. Okay, and that's okay, right? Wait a second, there's something wrong. Negative 10, there we go. There we go. So when we do that, we get inf, right? Because x to the very large number is not very good. Also x, actually, no, this should be negative. I said negative number. Yeah, a should be negative. So actually this is not so bad, right? So it's just 0, so you don't think that's a problem. But then when you try to do it by this sum, then a sum of zeros is going to be 0. And then so you take 0 divided by 0, and that's why you get inf. Okay? So that's why this produces nans. So then you do this little trick, okay? So you say, all right, we're going to take this exponential of a value over the sum of the exponential of the values. We're going to multiply it by this quantity that's equal to 1, right? It's just exponential of some number negative b over the same exponential of some number negative b. And then thanks to the rules associated with exponentials, we can move the b to the inside. And so now we have exponential of a to the ai minus b over the sum of exponentials of aj minus b. Okay, so this should be pretty clear to everybody. I didn't do anything magical here. There's nothing that magical here. So then the key point is that b can be any number, and this is still true, right? So we can take this exponential, subtract b from every single value, and then compute the exponential, and then divide by the sum, and we'll come up with exactly the same answer. So it's actually a very common. Why is that text max? Text around? No. Okay, well, so it's common to pick b to be the maximum of all the a's, and what that has a result of doing is that one of these values is going to be x, at least one of them is going to be exponential of 1, right? Or exponential of 0, right? Because if ai is equal to b for one of these ai's, then that value is going to be 0, right? Because the same value minus the same value. So you get 0, and then exponential of that 0 is 1. So then when you're doing the sum of exponentials, it's going to be at least 1. Okay? So then you're never going to divide by 0. So that's usually why people do that. So at least one term in this probability vector is going to be at least 1 over something. And then so if you do this, you feed it exactly the same ill-conditioned values a, but then you pass in this b, you subtract it from everything, and it works as expected. Right? Okay. All right, so that's about it for the things that you really should know to do this assignment. Are there any questions about anything that I've done? There's basically a k-means section at the top. You're gonna generate these really scary looking faces. You're gonna, evaluate the clusters that you generate. Yes, they're really. This is, when you do k-means on, if you compute average faces, that's what an average face looks like. You're going to do the same thing with the Gaussian mixture model, which you also learned about. The Gaussian mixture model is going to take a lot longer to run, so k-means will finish in like a couple seconds. Gaussian mixture model, I think it took about, for just computing 5 clusters, if my implementation took about 8 minutes. Okay, so this is what I'm talking about. You got to make sure you don't do anything terrible. And then, yeah, you end more creepy faces. And then there's this face classification contest, okay? So basically what I've done is I've given you pictures of George W. Bush and Colin Powell, and you have to figure out which one's George W. Bush and which one's Colin Powell, okay? And that is the contest. You have to do this with at least 80% accuracy, right? So 80% accuracy is the baseline just to get credit on the homework. And if you remember from lecture, Zico mentioned that a common thing people do with k-means is to use k-means to select RBF features, RBF centers, as like a first shot. So if, as it turns out, if you do that, you'll get 81%. So that's the baseline. So this but that's what you're going to have to do. You're going to need to copy over your SVM implementation from the last homework assignment. If your SVM implementation is pretty slow, I advise you check out the solutions from the last homework. Yeah, so our SVM implementation, the objective is just 1 line. Your gradient is 2 lines. Your train is a for loop with 1 line, and then there's a verbose parameter. And then your predict is 1 line. Okay, so these are all using matrix operations, so it's extremely efficient. It's impervious to both sparse and dense operations. So, you should check this out if you've struggled on the SVM assignments and you didn't write it. FCM is supposed to be a pretty simple thing to write. Everything else from now on is going to be more complicated. But yeah, you're gonna need to copy over your SVM for this assignment so that you can do classification on this problem to figure out which one of these pictures is George Bush and which one is Colin Powell. Okay. And so so actually really do check that out so you can see how we did it, because it's really important to know how to do these matrix operations. But the rest of this recitation is basically just extra things that might help you getting to that 80% threshold on the contest. So there's this thing called, so in learning rate for gradient descent, so when we do gradient descent, we just sort of picked a learning rate at just sort of arbitrarily, try different ones and see which one works. We also just picked a number of iterations, just tried it and see what works. And so there's this thing called the decaying learning rate where we shrink the learning rate as we progress, right? So we can consider this a very simple example of y equals x squared, right? Then your gradient is just x squared. Your objective is x squared. Your gradient is 0.5 times x. So we can pick learning rate is 100 iterations starting at 20, and then we just run gradient descent, and it works pretty well. The minimum of x squared is at 0, right? But then if for some reason our learning rate would happen to be like 50, then it blows up, right? And it doesn't converge at all to x equals 0, which is the solution for x squared, right? So what do we do here? So depending on the size of your learning rate, this update could be too big to converge. And if we have a constant learning rate, then when you get close to the optimum, it might end up becoming too big and then overshoot, right? And then so you'll see this when you're plotting your objective over time, and then it'll decrease, and then it'll pop back up again to some large number because it took too big of a step. And then so what you did in the past, I guess, is just tweak the number of iterations to make sure it's not too big. But instead, we can have this idea of a decaying learning rate. So then every time our objective doesn't decrease, we multiply our learning rate by this factor of beta. So in general, people use beta equals 0.9. So every time you don't decrease your objective, you decrease your learning rate by multiplying it by 0.9. All right, does it make sense? It should make sense as like a general idea. If I'm going to go too far, then I'm going to shorten my step size by a factor of 0.9. Okay. And yeah, in practice, 0.9 works quite well. So this is not actually a very big difference to the above algorithm. We just we save the initial starting point and the initial objective. Oops. And then we take a step with the current learning rate. And then while we don't see an improvement, we're going to multiply by beta and then redo that step. We're basically going to redo the step and then shrink our learning rate until we see an improvement. And then and then when we actually see an improvement in our objective value, then we actually take the step. Okay? So it's, it introduces like this short while loop into your SVM, but if you do this, then you no longer have to tune your learning rate. Right? You can just set learning rate to be some value, and then it will shrink according to how far you progress in your SVM. Okay? So, this is to decrease the number of parameters that you have to tune, which is normally a very, very good thing. Right? You want to spend less time tuning parameters and more time trying different things. And then the other trick that you can do is these early stopping conditions. So for gradient descent, you could run for a million iterations, but like maybe the last like 900,000 of these iterations were like basically at the optimum doing nothing. So, you can actually just detect when you're doing nothing, and just break out of the for loop, and that's exactly what early stopping is. Right? So none of these are terribly complicated ideas, but these are just things that people have done to these various iterative algorithms. So, instead of guessing the number of iterations to do, you can just set a very large number of iterations, and then when it's done converging, just have it, when you find this early stopping condition, then you just terminate and break out of the for loop. And so for gradient descent, normal stopping condition people use is when the gradient itself is small, right? So when your gradient is really, really small, then you're not going to move very far, right? If you do the update with a very, very small gradient, then you're hardly doing anything. So you might as well just stop, right? That makes sense. So here, I take exactly the same code with the decaying learning rate, and I just add this thing. So then if the step that I was going to take is less than some really small number, then I'll just break out of the iteration. So now I can do this with the, I can give it a really big learning rate, give it an abnormally large number of iterations, and run it, and then it'll stop after 488 iterations, and it converges to an optimum. So by doing this, I've effectively removed the need to test both of these parameters. Right? I no longer need to test. I no longer need to tune learning rate, and I no longer need to tune the number of iterations. Okay. So, but it's normally good to still have the number of iterations as like a endpoint. If you don't want your function to run indefinitely, because maybe it just keeps. Maybe it's possible that it optimizes for like 5 hours, but it doesn't really quite meet the terminating condition. But you get good enough results after like 5 seconds. So it's still good to have the number of iterations, just so you can have it stop after a certain point. But if you're gonna make no progress at all, you might as well stop. Right? So these are two very small modifications that you can add to your SVM code. One's just adding a for loop. The other is just adding an if break. And you don't have to tune these parameters anymore. Yes?
Does it make sense to compare it with the previous optimal relevancy if there is not too much?
Yeah, so that's another way you can compute whether or not you're going to stop, right? You can say, okay, this is where I was before, this is where I am now, how much did I decrease? If this decrease was small, then I should probably just stop, right? The only problem is that this now depends on the scaling of your objective, right? So, if your objective, is working on the order of hundreds of thousands, then maybe a small number is true that, it's not really doing anything. But if your objective value is on the order of like, 10 to the negative 6, then detecting changes of 10 to the negative 6 isn't really going to be indicative of when it's going to stop. But the gradient is going to be on your parameters. Now, in the end, yes, that also depends on whether or not your parameters are well scaled, but your parameters are generally more than just one objective value. So collectively, they tend to work better. than the, well, the gradient is going to be a gradient of multiple parameters. So it's going to be a vector, and so the chances that all of them are going to be ill conditioned is not so bad. Okay. Anything else? Okay. Oh, wait, there's one more. Last one, okay, I promise. So there's the last one. When you do RBF features, right, you have to, and you do this median trick, then, you need to do all these pairs of clusters and compute the distances and take the median, right? That's the median trick. So to get all pairs from an iterable or a list or something, then you can just use itertool.combinations, and then it'll return all the pairs. So here I give it a range of from 0 to 5, and let's see. Yeah, and then so here it just gives me all pairs of all all elements in the list from 0 to 5. So, and then you can take the median of this by using this. Right? Okay, that's the end of the notebook. Are there any questions? Okay, you're free to go. Good luck on the assignment. I hope you enjoy it. It was